is what we are doing at 9T Labs. I mean, you might have heard our name or not. We will do the introduction properly and basically showing about our additive fusion technology, which is a stack of technology we are developing in Zurich since 5 years. Showing, of course, what we do today, so where we are at, but also looking into tomorrow and together, I mean, with you attendants, also gathering some ideas, some comments. I mean, we want it to be very open. So feel free also at the end to give feedback or to share potential opportunities where we have maybe not explored anything. So that's, I guess, from the setting. I mean, myself, my name is Yannick. I'm a business development manager here at 9T Labs. From a background, I was 15 years in composites. I went to engineering university, so always in this field of high performance parts, and therefore trying to push the boundaries now at 9T Labs.
And as Yannick said, you can go to the next slide, Yannick. So today's presentation is from 9T Labs, hosted by Modulus. So we're a growing community for the materials space, so specifically dedicated towards the materials industry. So it's a new platform that's been launched 6-7 months ago. So we're fastly growing a merging community around the materials space, and this is a part of what we call the speaker series. So happy to host this with 9T Labs. A few things before we get started today, just from an administrative point of view. Today's webinar is going to be recorded, and it will be made available following the presentation today. We'll also be doing certain snippets or highlights from today's recording, so you guys can have access to that and can pass that along to other friends, colleagues, partners in the industry as well. That's going to be made available on the Modulus community page, so we'll post that and certainly put a link afterwards so you guys can have access to that as well. If you're not a member of Modulus, it's free. You can join up that way, and we'll go through that at the end as well. As Yannick explained, today we hope for it to be an interactive webinar. So Yannick's going to go through the 9T Additive Fusion Technology, but we really want to engage with some of the people on the calls or all the people on this call today just to get some of your feedback, maybe where you see market opportunities, new applications, or potential barriers as well. So it's a learning experience for everybody. The structure, 20 minutes presentation, and then that's followed by the Q&A that we just talked about, more of a discussion, less of a Q&A. And then we can, at any point throughout the webinar, please use the chat button at the top to post questions. So we'll keep a running dialogue and we can work through those at the end. And then certainly when Yannick's done presenting in the Q&A session, everybody's mic should be enabled. So you should be able to open your mic and ask questions. So with that, Yannick, I'll turn it back over to you.
Sure. Yeah, thanks for the housekeeping. Regarding agenda, very quickly, I will go to 9T Labs directly, who we are, what we do, why we do what we do. Then I will obviously introduce the technology, so that's a result of our work, and then deep dive with some application example, because this always helps to really understand the different pillars of this technology. So 9T Labs, very briefly, I mean, was born 2018 in Zurich, Switzerland. It's a spin-off of the ETH there. Up to now, we have funded over 22 million euros. And we have around 70 employees. Most of them are based in Zurich, Switzerland, where we have our headquarters. We also have a few colleagues since last year in Lowell, Massachusetts, so just north of Boston. In terms of, I would say, major advancement in the company, we received some awards. You can see them here, both on sustainability, design topics, but also going to be, certified already ISO 9001 and going for other certifications in the future, depending on the industry. So what are we doing at 9T Labs? We call this stack of technology, you will see it's a suite of technologies, hardware, software. We call it AFT, so Additive Fusion Technology. And I think that's something as engineers or even non-engineers we can all agree about. As a starting point, it's really about making better performing serial parts. So we really want to scale this topic using significantly less resources. So it's really getting high performance while maintaining the sustainability point, if one can interpret it like that. What does it mean? I mean, the software is kind of hidden, but I will come back to that later. In terms of hardware, we have two machines, two modules. One we call build module. It's where parts are built physically out of a code. It's based on the 3D printing principle of continuous fiber. And there is some specificities in terms of input materials. We will also describe that a bit later. And once this preform, which comes out of this printer or this build module, is finished, we bring it to what we call fusion module, which is kind of a compression molding process where we can then finalize the part in properties, but also in shape. That's here the full stack. So you see there is 4 main pillars in developing such a technology. Obviously, we wanted it to be very digital software oriented because you can optimize a lot while not doing physical parts. So we speak about this digital environment where we design the part based on an envelope and based on load cases. And after having designed the part, there is a plugin to immediately simulate and iterate between design and simulation. Once we are done here and we have an optimum design, we generate a G-code, which is basically the code which will be sent to the build module. Before jumping to the machine part, let me mention quickly the material part. So that's also a key decision when starting to build such a technology. We decided to go full in on thermoplastics and obviously having an open system. So we are not having some proprietary 90 labs materials. We use off-the-shelf materials, both in the long fiber materials and in the pure filament, I mean, neat thermoplastic filament. Then we go to the machine. Obviously here it's all about automation and also having least waste possible, because that's what is interesting in additive: high resolution, low waste or no waste, depending on the parts. And last but not least, to really scale the topic to make hundreds or thousands of parts, high quality, consistently, and also having the possibility to consolidate, reshape, integrate metal inserts, for example. We chose to do this kind of compression molding we call fusion. So here, just a few examples of what is the advantage. I mean, at the same time, you already see one of the fields where we are active. It's bringing some key benefits. One is reduced carbon footprint. That's really about decreasing weight during production, decreasing waste, sorry, and then decreasing weight of the final parts so that in use they are more efficient. On the other side, also having lowest cost for best performance. That's why we rely on off-the-shelf materials, high automation grades, so that we can, while being very high performance, have decreased costs versus, let's say, even metal parts. And then extreme lightweighting, which comes with the first point I was mentioning. It has a positive impact, mainly during the use of the parts. So what are benefits versus metal parts? This is one example you might have seen when you look at 9T-Lab's contents. It's a helicopter door hinge on the left side, which has been actually printed and then fused with our solution at the end compared to the benchmark part, which is currently on the helicopter. we speak about 50% reduced production costs, 75% weight reduction, and even increase mechanical performance, which would basically mean we could even decrease the amount of material more because we don't need to overperform on such a part. In automotive, so ground mobility sector, we are also looking at different parts, obviously, because of the volume starting in the high performance cars, but then also looking at this base to then increase also the volume production over time. So you see all these parts which are structural, highly loaded, but might be structural plus aesthetical, like spoiler supports. Some other parts are more hidden. But here also working actively in this field, you should see some parts coming to market in 2024. Market which is way faster in pace and also resonating with a lot of us because some of us come from cycling, competitive cycling, and it's a market where it's way faster to go into. So within 6 months, if complying with the quality requirements of the OEMs, you can have something in the market, which is also crucial for a startup, obviously, to prove the point of scalability. Here we are working on saddles, rocker arms, brake levers, and other bike components, obviously given the smaller envelope of the printers and also the shape doesn't make sense to print with our technology, at least a frame, but really to make the point on structural components. Motorcycles, I would say, is also a two-wheel application, even loaded higher due to the speed and weight of such machines. Here we have already shown this year that we worked on a rocker link on the rear suspension. This should also go to market by next year. It's very interesting applications, obviously validated at the higher standards and then giving us also good confidence to move into cycling and automotive. So coming back now to how we make those parts, and this is a build module again, a bit more visible what is inside. So you might see there's a deposition head with a red triangle within this, this machine. And this deposition head, you see it here. It's about depositing two kind of materials, or two kind of input materials. One, the continuous fiber tape. So you see this semi-open deposition feed, which is helping us to guide continuous fiber tape where we want to be to place it on the parts. It's a big advantage of the system here. So we have a high resolution. We really put only continuous fiber where we need the reinforcement, meaning that over the entire part, we might have way less continuous carbon fiber than traditional composites while maintaining the performance. And the way we developed this deposition foot is such that we can even kind of rotate this deposition feed and therefore avoid any fiber distortion in the tight angles or around holes. And on the other deposition foot, we are bringing a pretty classic 3D printing filament, either neat or short fiber reinforced, so that we can mix, as you see on the drawing at the bottom right. We have some strands of continuous fiber going around the holes in a kind of H shape, and the remaining material is here printed in short fiber reinforced plastic. Of course, we have to pair both polymers, need to be compatible. Here, to even increase speed on some application, we would actually only print the continuous fiber material, bring it to molding and over inject just to gain in speed. versus 3D printing. But that's always to be assessed on performance and costs. Correct. And then we come to the fusion module, and then big question, why don't we stop after 3D printing, and why do we go back to having some non-recurring costs with molding, etc. There is a lot of reasons, actually. There are a lot of reasons. One being the reshaping possibility or the welding possibility, also with thermoplastics. So that here, as an example, it's this rear rocker link for the motorbike suspension. We print this shape flat, and then we can reshape it in this fusion process, and even co-mold it with some organo sheet, which will give us some higher performance in torsion. So long story short, here, what do we do in the fusion process? You see at the bottom, in the middle, how the structure looks before. So after printing, you still see quite some porosity. It comes from the material itself. Tapes are porous to a certain point. It comes from the deposition, obviously. And you also see at the surface, it's not flat, meaning you will also see with your eyes some layers, meaning the interlaminar strength is far from perfect. What we want is what is on the right, and that's how it looks like after the consolidation phase. Really a part without or with less than 1% porosity, very flat surface, and these kind of parts can really go into high performance applications for a longer time. So we speak also fatigue cycles and so on. So the flexural strength, if you take some sampling, you see that there's a huge increase. So it's just a different class of performance. On the right side at the top, you see how we would approach such a part. Such a rocker link has 3 attachment points where we would put inserts, metallic inserts for the interfaces, and around those 3 points, we do these loops, which are printed with continuous fiber. The remaining of the material is neat or short fiber reinforced. Then we place this shape into the mold, and while applying pressure and temperature, doing the consolidation, increasing interlaminar strength, reducing void, we also reshape the part to the final shape, as you see here a bit. Correct. So that's basically running you through the process, the really 3-step process. We develop, optimize, validate in digital. Afterward, we create a physical part by material deposition through 3D printing, and we use this one or many printed parts to be brought together and consolidate, reshaped in this final fusion step. So what kind of markets are we working on actually? I mean, I was showing a few pictures. Obviously, aerospace interiors is one of our scope. Another one are obviously high-performance sports, so cycling, some water sports topic, some snow sports. We work on some automotive applications, but then there is many other fields. I mean, some we are already exploring, some we would also listen to the crowd basically and see if there is more fields or if there is some confirmation here that robotics or eVTOLs or medical applications, satellites, wearables, whatsoever. I mean, here I would give the word to Adam first, and then of course to you attendees first ask questions if something is not clear, if you want some more details about what we do, and also happy to listen about where do you see some potential applications. Thank you.
Yeah, thank you, Yannick. Yeah, I think we did have several questions that were coming in as you were talking. So maybe we start there. I think there were just trying to get an idea of conceptually the capabilities of the technology. Marcel was wanting to ask the range of series size that can be produced these days. So what are the ranges, minimum to maximum of the volume of parts that you guys are producing?
I mean, typically, I would say between 1,000 and 100,000. Obviously, it has a lot to do with the geometry. It's different if you do a watch case for a luxury watch, or if you do a component for a plane seat. So just the capacity of the machine will be used differently. And then on the lower side, why we say 1,000, might be 100, but you just have some non-recurring costs, which will be engineering for very new parts, and which will be tooling. So to amortize this, some application in space might be even lower than 100, but in general, we would say between 1,000 and 100,000 is a good fit for now, given the speed and costs of the technology.
Sure. Yeah, and I think a follow-up question to that is just the max dimensions that you would consider, what of the build and the build module and the compression module.
Sure. I would say we always say a shoebox, so it's 35 by 27 centimeters. So the printing surface by 25 in height, but the height you can compensate through also co-consolidating different preforms. And obviously the fusion module is accommodating whatever comes out of the printer, so they are dimensioned so that it's compatible. So yeah, if you remember a shoebox, that's a good indication.
Okay. Yeah, and then I think we're starting to see some other questions on polymer types. We got 2 on different polymer types here. So what different resins or polymers, and then specifically, can you print PEEK, PEC, PEI, those types of polymers? So kind of 2 questions, just generally, what's the range? And then I think it got more specific on the PEEKs and PECs and PEIs.
Oh, makes sense. So as I said, I mean, it's all thermoplastics. Here we have actually currently a lot of experience with PEC, PA12. That's the main ones we are using. But as I said, it's an open system. So mainly when we start a project with a customer, the customer might have, I mean, we speak about big OEMs, they already have some materials which might be even certified for their industries. And then we are open to the point that they tell us, okay, I have a certain carbon fiber or a certain tape already, which is qualified. Then we source this material, we identify the parameters on our machines, and then it's way easier. It's also faster for us to go into market with those customers. So we have already looked at PEEK, PEI for sure, PA11 as a biosourced, let's say, alternative to PA12. And in terms of fibers, here again, it's very diverse. We work a lot with carbon because that's what the customer mainly asking, but we are also looking obviously into glass fiber, Kevlar, also basalt, maybe as an entry point to this kind of biosourced fibers, but with a higher temperature resistance, obviously. So I would say it's pretty broad, more on demand, if it makes sense for the function required.
Okay. Yeah, I think the converse question to that is, or the complementary question is fiber type. So there was another question around, a lot of what you displayed was carbon fiber, but specifically this question is asking about natural fibers, flax and hemp.
Oh, I mean, sure. I mean, that's a question we often have. In general, I mean, most of the customers who are scouting for new technologies or new applications, they go in from the very high performance part. So they come a lot with carbon fiber topics. Obviously, the sustainability trend is also pushing a lot of people to at least explore all these natural fibers, as you say, flax, hemp. Here, say it's always a bit a limitation. You can exclude the high performance thermoplastics because if you go at 380, 390 degrees to melt them, your natural fiber will just not cope with that temperature. So then you can look at, I mean, some markets are interesting. For example, recreational markets, you can work with PAs and natural fiber. So of course, looking into that on some of those specific market applications, because here's an interesting point is how to make these natural fibers work in a structural way. Because nowadays we see a lot of those applications in composites which are non-structural, but really how to use a high resolution of such technologies to bring structural behavior with natural fiber. So that would say would be an interesting challenge to look at.
Okay. Yeah. Okay. I'm gonna jump over to a more strategic question, and then I'll come back to a materials question, just because I want to make sure this gets answered. So Sean De Silva asked, "Who is your competition?" So do you consider Mark Forge your competitor, and how do you stack up? So that's a multi-part question there.
Sure. I mean, basically, you can do your research, and the definition of competition is always interesting. I would always consider a timeline behind. So competition today, when we are asked by some customers to make a proposal, mainly, say to 80% of the time, we compete against metal parts. So there, the competition is super broad, super established, incumbent players. They have built their fences. And I would say that's the biggest challenge if you really want to have a big market for this type of new technologies, because we speak about sometimes new certification. I mean, it can take quite a long time if you look into medical or aerospace applications. Then, of course, fast forward on the timeline, who is working on similar full stack solutions, pushing on software, so both design simulation or this digital twin topics, who is working on higher automation, software integration into machines, and so on. And then, yeah, you get it. I mean, you named some of them. Some of them are not directly competitors because probably from a strategic point of view, they see other markets being more interesting. If they have a bigger portfolio with metal and polymer 3D printing, for example, they might see more potential short-term on growth in metal 3D printing. But yeah, then I would say in general, it's always good not to be alone for too long into a field. So it's not bad to have some competitors. We all know each other because it's a small field, thermoplastic, automated material deposition. You can also consider AFP, ATP, or these automated tape placement solutions being pretty similar from the philosophy. Then it's about resolution, of course. And then it's really about making the pivot. I mean, it's really going into the market, making the point, proving that it's first doable to replace some metal parts with thermoplastic, I mean, reinforced thermoplastics. And second, that it's possible to scale. So also the economics behind, because one is, of course, a technical point, but the other one is economical point. So yeah, for sure, not boring also on making the competitor landscape and seeing the dynamics here. But yeah, rather trying to grow the pie, and then we'll see how we split it.
Yeah, I guess I'll get back to a more technical question, and I think it relates to, you know, one of the things that you showed in the presentation is, you know, the limited scrap, right? I mean, it's a high utilization of material that lends itself well to sustainable and circular processes and parts. Marcel is specifically asking then, you know, is your experience using bio-based polymers such as PP and polyethylene?
Yeah, I mean, not using PP polyethylene, because on this topic, we are working on several pillars. Obviously, just because it's additive, it's already reducing waste. Then it's looking, of course, at the in streams. So what comes in as materials, and here because we are also looking at material costs. So it's also about what is in high volume in the market to make it a competitive case. And obviously those, let's say, newer materials or biosource materials are not on the market at the same scale. So that comes also sometimes at a different price point, and the willingness of the final customer to pay a premium and so on. So it's, let's say, it's an equation with many variables. But where we can certainly have an impact is on thinking about how to also optimize the material stream. So if we cannot, because we are in high performance, we need to take a peak or a pack, we cannot take a biosourced peak or pack now, and we need a virgin continuous fiber, maybe, then what do we do with this material at the end of the life? Because there we have a responsibility. I mean, when I say we, is our final customer, or the OEM, and ourselves as a technology provider. And here we're working on interesting concepts, I guess, hybridization, which we can achieve with printing, and then consolidation is interesting because we might just print 20% of a final part in volume, so kind of very precise preform, and then co-mold it with 80% of chips, of carbon fiber chips, shorter, which might come from shredded parts, which we made ourselves. We have done the tests. We have done a sustainability report with some LCAs, including this topic. So you can just go on our website and download this report to get the data behind. But there is really about mixing different streams of material to get a part as circular as possible from the material perspective. On the fibers, it has been demonstrated a few years ago in the US in a big project. We are also working on that. It's basically taking parts, shredding them, taking these shorter fibers, commingle them again, and create yarns, which are continuous, non-continuous material per se, but being in a yarn entangled also reach very interesting structural properties. So we have many different things to explore, always together with customers, and happy to share more in detail in a separate meeting.
Yeah, absolutely. I think it's probably a whole webinar unto itself, right? I mean, it's
if you go into material science and so on, it's very interesting, sure.
So we got a couple more questions coming in too. So one is, I'll save the one from Sean for a minute, but another one just common lead time. So from a first discussion to a prototype, what are typical? And I know there's a lot of variables, we all do, but just generally speaking, is it weeks, months, that kind of thing?
Sure. I mean, besides the administrative topic, because I don't want to mention that, I mean, this is just depending sometimes on the companies about NDAs and contracting and terms and conditions and so on, which can actually really double or triple the entire time. But let's say what is feasible, just, I mean, physically, theoretically, if you take, I mean, engineering, if you take it serious, you do understand all the boundary conditions, the envelope, the peripheries, and so on. You probably count 4 to 5 weeks, of course, it's really depending on the application. Then you need to, once you have frozen the design, you need to design and order the mold, which you can also, just to be on the safe side, consider, say, 8 weeks. And and then you start your production. So maybe from first contact to first parts, let's say 3 to 4 months is already good, but this is acceptable if you want to go into serial part production. That I would say that's pretty fast actually.
Mm-hmm.
So I would say that's plus minus some corridor we would give.
Okay. So the next question gets into it's more of a commercial question. So Sean is inquiring the average system cost. So
so I'm pretty open. I mean, the system cost is 250,000. This includes the software, so both the design software and we call it production suite. It's really this kind of ERP system which is managing the data flow and the machines from a firmware perspective. And this includes, of course, 2 machines. You will also have some basic material at the beginning to start with. You will have some support, some training. I mean, these basic things you have when you start with a new technology. But yeah, 250K is what you can remember.
Good. So one question, and I'm going to put it in the chat now, and then you guys, everybody on the call can respond to it. And I've got some questions I'll ask Yannick that I think everybody should also be aware of and know. But the one thing Yannick and I were discussing and prepping for the webinar, I said, I used the word 3D printing, and he stopped me and said, it's not 3D printing. So I'm just going to post the question and you guys respond back. What do you, when you came to the call today, did you think 9T Labs was a 3D printing company, or did you see them as something else? So just kind of general market feedback a little bit there, just as a quick question. So I'm going to ask, do you see 9T Labs as a 3D printing company? And then while you guys are responding to that, I'm going to ask Yannick a couple questions that I think are important for everybody here to be aware of. So we went through the range of polymers. We're talking about the process capabilities, but we touched on it real quickly, and Marcel had some great questions around biopolymers. But with the push and increase in circularity and sustainability, are you seeing, from the traditional composites field, is there an interest in your technology? Is that helping drive more interest in 9T Labs, just because it's such a much more efficient process than the traditional composite manufacturing processes? Is that playing a role in your success at all?
Yeah, I mean, it plays a role in 2 ways. Obviously, it depends a bit where they place those kind of technologies on their roadmap. Say, one point is for those who have never done composites, it might be a good entry point. So they would go from metal to thermoplastic composites without going the thermoset route. So that is one thing we see in the market. The other thing is, obviously, if they are with thermoset, higher volumes, and let's take sports, but it's valid for most of the industries. There is also the topic of supply chains, geopolitics, and we all know that a lot of volumes of thermoset come from Far East. We have all gone through COVID with some challenges. And of course, at the end, it needs to reflect into the economical models also, because still, even though we are just a few months post-COVID, people have already forgotten quite a lot of pains in supply chains, and they just go back to their established suppliers and nice pricing. But yeah, long term, there is all these uncertainties, and also wanting to reshift production to the US or to Europe. And there, it's really a trigger point also in discussions on strategic roadmaps of supply chains. That's for sure. But it's also about balancing what is necessary now and what is nice to have in the future, because that also steers the development budgets, which basically are also financing these new solutions.
Yeah. Okay. Yeah, I just trying to understand if that's helping push opportunities your way.
Definitely.
So just an interesting question. You showed us a couple different applications, but what is maybe the most challenging application that you guys have had to work on, just from someone said, hey, can you do this? Maybe how you guys went about that.
I mean, there's different ways to define challenging. I mean, one thing for sure is in aerospace, very challenging because you have such a list of requirements and things which, yeah, they are just like they were forever, and sometimes you just need to. It's always a pain to replicate what has been done in metals with composites because you might just prefer to redefine a bit the testing and the boundary conditions. But there's a challenge really to comply with all what is given. And then the other extreme is if you go into cycling, for example. I mean, people have no real list of requirements. I mean, there is, of course, there is some DIN norms you have to comply, but I mean, all,
Right.
I would say, high performance bike manufacturers, they go way beyond that. And then there is internal tests, but the internal test for OEM 1 is different from then OEM 2. If you ask for clear load cases, you often don't get them actually. So it's a lot of, oh, it works with this geometry and this material, at least try to replicate it. And there, the challenge is actually you starting a design without knowing the real, the worst conditions in use, isn't it? So that's also a challenge as per se if you don't really get guidance and you then need to start apart from kind of benchmarking with existing. So yeah, I would say those are two very different kind of challenges, but still also influence on how fast you can implement.
Okay. Okay. And so some suggestions here, and maybe it's a question and a suggestion for new markets. Have you looked into defense and military applications? Is a question from the audience.
Yeah, sure. I mean, have we looked? Certainly. I mean, this is always, especially if you're in aerospace, the big players in aerospace, they all work in different fields, civil, defense, military. Yes, especially being Swiss and European, we are often, at least we tend to be a bit shy on going into this for philosophical value reasons.
Yeah.
It might have changed a bit because we have a conflict in front of the door for a few months now. Very different approach in the US, where also the way to finance innovation through Department of Defense budgets, even if it's civil applications, is often dual applications. And so it's a cultural problem. I would say cultural topic as such. So up to now, we are not certainly active. We get some interest. I mean, we get some requests from potential customers on some parts we know they are meant in this field. So we are not actively working on it. On the other side, we are not closing the door. I mean, we also need to focus our resources. So we are very systematic in how we select a field, and we know we cannot do too many fields in parallel. We have assessed medical instruments, for example, very interesting market, but we can not for now cope with medical and aerospace certification in parallel with our resources. So we just go aerospace, a field in aerospace versus doing too many things in parallel and not closing any chapter. And as such, I mean, defense military is in this matrix of assessment. And if it's more interesting in terms of time to market and potential mid and long term, we will assess it as others.
Okay. Yeah, I guess as an American citizen, I didn't consider that Swiss's position in the geopolitical scene, and as it relates to defense. So that was that's something interesting that I just took away now. So that's So I guess another question is, we've got some people from around the world here. Where can they see your technology? So seeing a presentation, sitting on a webinar is fantastic, but how can they see this in person?
I mean, in person, It's very simple, either at our facilities. So we have two facilities. One is in Zurich, Switzerland. The other one in Lowell in the US. So both facilities have machines. And if you're wanting to see them, you can for sure contact us. We can arrange something. The other way is on the main fairs. I mean, we have two main fairs, say two events where we show our machines physically, one being ChemX. So ChemX is just a month from now, roughly. So there you will be able to see our machines, of course, and the parts which are coming out of them. And the next opportunity is then in Europe, JEC World, which is in March, where we also show our machines every year. So those are four possibilities, basically. Two sites from 9T Labs and two fairs.
Excellent, excellent. I do want to be respectful of everybody's time. We're coming to a close. Are there any last questions? It looks like Sean's typing. See if we got one more question. While he finishes putting that question through, once again, I mentioned at the beginning here that all of this will be made available on Modulus. So we're going to make sure that we take the video and then we'll also do some short clips. So if there's certain sections that we want to highlight, we'll put that up there as well. It's accessible to everybody. Just join Modulus and you can see that there. So we'll send links out to that as a follow-up to everybody that attended today. And then, of course, Yannick, if you want to go to the next slide, everybody can please reach out to Yannick directly with specific questions or opportunities. So if you've got something specific you have in mind, reach out to Yannick. All his information there is available. So Sean is one last question. He says, will the pitch be made available? Yes. So we just answered that. We'll also send that out after the call as a follow-up to everybody that attended today and everybody that was either signed up or wasn't able to sign in today as well. Looks like we've got one more question coming in, Yannick, before we sign off here. Anything while Marcel's typing you want to close with from your side?
I mean, for me, it's really about making people understand better what we do and why we do it. So for sure, I would appreciate if some people from today's webinar are coming to ChemX, coming to JEC, Zurich, that we can meet personally, that people can have the parts in their hands. It always makes a difference to really see, because basically also coming back to the comparison question and what's the difference between our technology and others, and having parts in your hand, that's the best way to show the differences. And there is no better or worse, I would say. There is just different business cases behind. If you really dig deep into the analysis of the companies, we are approaching different markets in a different way. So it's actually not that much overlap if you go deep into the tech analysis and the commercial analysis. But yes, all those points, that's the reason why we do webinars, why we do articles, why we communicate on LinkedIn, on Modulus, why we go to fairs. Is really a part of the game in innovation is education. And I'm happy that we put another stone on the education wall today.
But it looked like you changed a couple people's minds. They had the same perception I did, but it looks like you've changed a couple people's minds in terms of who 9T Labs is and the capability of your technology. So it's definitely a positive.
All about great. Making an impact, isn't it, Adam?
Yeah. It's it's one at a time sometimes. But yeah. I want to thank everybody for their time today. We know that time is a valuable resource, so we do appreciate you guys giving us yours. If you have any questions, there's multiple ways of getting a hold of Yannick, as on the screen here. Multiple ways of getting a hold of myself if you have any questions there. Look forward to keeping the conversation going. So please join Modulus. Please contact Yannick. And let's keep moving forward with this technology. So, but thank you for your time, and we look forward to speaking with you maybe in a future webinar. Thanks, guys, and thank you, Yannick.
Bye bye.